graduate mentor for the P2EP program. I'm a PhD student from NC State, working under the supervision of Dr. Marian Lila and Dr. Massimo Urizo. And so I want to tell you about blueberries. So blueberry is already a very popular fruit in the U.S., and it's grown increased attention in recent years as consumers become increasingly aware of the health benefits associated with blueberry. So part of the reason for, I'm so sorry. So blueberries are particularly lacking in genetic resources. So blueberries are a very popular fruit in the U.S. and it's grown increased attention in recent years as consumers become aware of the health benefits associated with blueberry, including those related to the consumption of anthocyanins, which are a metabolite that are expressed in blueberry and they are known to act as natural antioxidants. Blueberry is a particularly rich source of anthocyanins, and despite the nutritional benefits associated with them, there has been little work done to understand the genetic mechanisms underlying the increased synthesis in blueberry. So part of the reason for this is that there's an overall lack of genetic resources for blueberries. So as the title of this presentation implies, this summer my interns and I have been working towards providing some of these genetic resources so that we can begin to understand why blueberry is so great at synthesizing anthocyanins. So before my interns tell you about the work that they've been involved in this summer on their specific work for the projects, I'd like to give you an overall background for the projects that we have. So project one involves creating a method that is designed for screening anthocyanin content in blueberry samples, specifically for the use in genetic studies. This will be used in project two, where we will use it to evaluate the anthocyanin trait in various blueberry germplasm so that we can begin to understand the natural variation that exists for the trait. This germplasm also includes specifically mapping populations, which will be used in our ultimate goal for conducting a genetic association mapping study. This can be used to identify regions of the genome that contribute to anthocyanin biosynthesis, and the ultimate goal from here is to find a genetic marker that correlates with the increased synthesis, and this can be passed on to blueberry breeding programs to either maintain or increase the anthocyanin content in future cultivars. So my interns are going to tell you more about the work that they've been doing this summer. But first I'd like to introduce them. This is Allison DeLange of East Carolina University, Jacob Verrier of UNC Charlotte, Robbie Morrison of Catawba College, and Lisa Azuo, who has also she's not a part of the P2EP program per se, but she has been working alongside us this whole summer, and she's been a very valuable asset to our team. She's a very talented high schooler student from the area, so we wanted to give her a special thank you. So with that, I'm going to let Allison take it from there.
All right, so as Kelsey mentioned, the first project involves creating a method for quantifying anthocyanin content in blueberries for genetic studies. The first part of that project is creating a method that is precise. So the current method used we refer to as the whole berry method, where berries are weighed out on a per gram basis and then used for extraction to quantify the anthocyanins. However, this could be a potential problem because anthocyanins, which also give blueberries their color, are only found in the skin tissue, so small berries may seem to have a higher anthocyanin content because they have more skin tissue and a higher surface area to volume ratio, and this is particularly a problem for a genetic study because this could lead to identifying genes that are related to berry size as opposed to ones that are related to anthocyanin content. So last year, Kelsey's group did a preliminary experiment where they harvested from 2 genotypes and separated the berries into small, medium, and large categories. Those samples were then quantified for both anthocyanin content and total surface area, and they observed that there is a tendency for anthocyanin content to increase as total surface area increases, with the samples. So as a way to try and alleviate that possible bias, what we refer to as the squeeze method was implemented, which is kind of as it sounds, you separate the skin tissue from the pulp tissue, discard the pulp, and then use the skins for extraction purposes. So in an expansion of that study, we harvested from 57 genetically diverse individuals that we selected and performed both the squeeze method and the whole berry method on them to see if there is a correlation between the total anthocyanin content and the surface area. Well, we didn't find a significant correlation for the whole berry method. We did see a slight positive trend as compared to the squeeze method, which has a smaller correlation coefficient. In addition to that, we performed a rank test to see if the genotypes ranked differently for anthocyanin content depending on which method was used, and they did rank significantly differently. So this leads us to believe that there could be a potential bias introduced with the whole berry method. So now Jacob is going to talk about the second portion of this project.
So the second component of Project 2 is developing a high-throughput method for screening large quantities of samples in genetic studies. So to give an example, take a genetic study with 365 genotypes. Typically in genetic studies, samples are measured in triplicate over multiple sites and over multiple years. In our example, it can hold up well over 6,500 samples, which is a large number of samples, obviously. So the traditional means of quantifying total phenolics, or anthocyanins, for example, phenolic compound, is HPLC, high performance liquid chromatography. HPLC requires lots of reagents, lots of times for extraction. It destroys the tissue, and it's about 77 minutes per sample for extraction and processing on the HPLC, which, for the previous example, is 6,500 samples. That's not feasible. So we're investigating a new approach, NIR, near-infrared spectroscopy, which requires far fewer consumables. It doesn't require a processing step and takes roughly 1.5 minutes per sample, which is 50 times faster than HPLC. However, to use NIR, we must derive a calibration curve. So using the aforementioned 57 genetically diverse genotypes, we derive this calibration curve. On the x-axis, we have the observed anthocyanin content, which is the content via HPLC. On the y-axis, we have the predicted anthocyanin content, which is via NIR. As you can see, we have an R-squared value, or a coefficient determination value, of roughly 80.7%, which suggests that our model accounts for 80.7% of the variation observed in this for anthocyanin content. This suggests that NIR is potentially feasible to be used for these large genetic studies. And now Robbie will tell you more about Project 2.
So like Kelsey said, Project 2 is about exploring anthocyanin content or variation in blueberry germplasm. So like Project 1, Project 2 also has two components. The first of which being we wanted to determine the anthocyanin content variability throughout the ripening season. And to do this, we conducted a time point study at Piedmont Research Center for 6 weeks, and on a weekly interval, we would go collect samples from 4 cultivars shown by the line graph on the screen. And the first time point is an unripe fruit, and the remaining 5 are all in the ripe stage. So as you can see, each cultivar shows a different level of variability. Some are more consistent while others show greater levels. And this means that it's cultivar-based, or to some extent, cultivar-based variability. But overall, we saw around a 0.4-fold change, so less than a fold difference in the highest and lowest concentration for each of the cultivars. So for the next component of the project, or Project 2, we wanted to look and determine what the heritability of the anthocyanin content trait was in blueberries. So to do this, we needed to analyze the mapping population. And last year, 2017, Kelsey and her group, they determined a blueberry population that would be suitable for a genomic study like this to determine the parts of the blueberry genome that are responsible for anthocyanin biosynthesis. So they went out and they harvested and they collected samples and they analyzed for anthocyanin content. And this past summer, we did the same. We went back to the same population and harvested and analyzed for anthocyanin content and compared the 2 years of data. So as you can see, in 2017, it showed a mostly normal distribution curve with a slight positive skew and about a 3-fold difference in the range of observed anthocyanin values. And in 2018, we noticed a primarily normal to bimodal distribution curve, and we also noticed about the same 3-fold difference in range of observed anthocyanin values. So using the tiers of data, we were able to determine that the level of heritability came out to be about 41%, indicating or corresponding to an intermediate level of heritability. So in conclusion, for Project 2, taking the two components, the fact that from Piedmont we saw less than fold change in the blueberry ripening process, and the fact that there's a 41 or an intermediate level of heritability, we can say that it should be feasible that we will now be able to determine the parts of the blueberry genome that are responsible for anthocyanin biosynthesis. And so we're in the back corner with posters 4 and 5. If you guys have any questions, I want to talk some more about blueberries, I guess. But thank you guys for your time.